Ever wondered how your phone's voice assistant recognizes your commands or how your email filters spam? This magic is all thanks to machine learning. It's a field of artificial intelligence that enables computers to learn from and make decisions or predictions based on data. It's almost like teaching a toddler, but instead of ABCs and 123S, we feed the computer algorithms with data. This technology is not just in your smartphones or email services, it's everywhere. From predicting weather patterns to recommending your next favorite movie or song on streaming platforms, machine learning is revolutionizing our everyday life. But just like teaching a toddler, the learning process isn't always straightforward. The success of these models hinges on how well they learn from the data. And that's where the concepts of overfitting and underfitting come into play. However, the performance of these models depends on how well they learn from the data, and that's where we encounter the concepts of overfitting and underfitting. Imagine you're studying for a history exam by memorizing every single detail from the textbook. You know every date, every name, every single minor event. You've got it all locked down, right? But when you sit for the exam, you find the questions ask for broader themes, connections between events and interpretations rather than specifics. Suddenly all those exact dates and names don't seem to help as much. You've essentially memorized the textbook, but you've missed understanding the bigger picture. This is a pretty good analogy for a concept in machine learning called overfitting. When we're training a machine learning model, we're essentially teaching it to understand data, much like studying for an exam. We give it a set of data, which we call training data, and the model learns patterns from this data. In an ideal world, these patterns would be the underlying truths, the broader themes that help the model make accurate predictions, but sometimes, our model gets a little too enthusiastic. It doesn't just learn the broad patterns, it starts picking up on every minor detail, every little noise in the data. This is overfitting. Now you might be wondering, why is this a problem? Isn't more detail better? Well, not in this case. When a model overfits, it's great at predicting outcomes for the training data. It's like knowing the textbook by heart. But when we introduce new data, which we call testing data, the model struggles. The minor details and noise it learned don't apply to this new data, and its predictions become less accurate. It's like memorizing the textbook and then struggling with the exam because the questions are different. The model has learned the training data too well, and it can't generalize its understanding to make accurate predictions for new, unseen data. So, overfitting in machine learning is when a model learns the training data too well. It captures the noise along with the underlying pattern, just like memorizing the textbook. Now think about studying for the same history exam by only skimming through the chapter headings. Let's dive into underfitting using this analogy. Imagine you have a big history test coming up. Instead of reading the chapters, understanding the context, the causes and effects, the intricate details that make the story come alive, you decide to read just the chapter headings. You're not really studying, you're more or less familiarizing yourself with the broad topics. When the day of the test comes, you find that you can't answer the questions well. The questions require an understanding of how events are linked, the reasons behind certain actions, and the consequences that followed. But all you know are the chapter headings. You don't understand the broader themes, the deeper details. Your performance on the test is poor because your preparation was insufficient. This, my friends, is underfitting in the world of machine learning. Like our history test scenario, underfitting is when your model does not study enough. It only skims the surface of the training data, failing to grasp and learn the underlying patterns and complexities. Just as the chapter headings were not enough to give you a full understanding of the events, a machine learning model that underfits the data does not capture the entire story the data is telling. It's like trying to understand a movie by only watching the trailer. The model sees the broad strokes but fails to understand the nuances, the hidden patterns, the intricate details that make the data what it is. An underfitted model is a simple model, too simple to make accurate predictions. It lacks depth, it lacks understanding, and it lacks the ability to generalize well from the training data to unseen data. It's a model that has not learned enough, a model that has not studied enough. So, underfitting in machine learning is when a model fails to learn enough from the training data. It misses the underlying pattern, just like skimming through the chapter headings. So remember, when it comes to machine learning, studying too little can be just as problematic as studying too much. It's all about finding the right balance. So, what happens when our machine learning model overfits or underfits the data? Let's start with overfitting. Imagine you've trained a model on a specific data set and it performs exceptionally well. Almost too well. It's mastered every nuance, every tiny detail of that data. But then, you introduce it to new unseen data, and suddenly its performance takes a nosedive. This is the consequence of overfitting. When a model overfits, it has essentially memorized the training data instead of learning from it. It's like a student who crams for a test, remembering every single answer from the study guide, but then fails when presented with a slightly different question on the actual exam. The model has become so attuned to the specificities of the training data that it struggles to generalize to new data, leading to poor predictive performance. Now let's talk about underfitting. This is when the model is too simplistic, and it fails to capture the underlying patterns in the training data. It's like trying to understand the plot of a complex novel by only reading every 10th page. You're missing out on a lot of crucial information. The result of underfitting is that the model performs poorly, not just on new data but also on the training data itself. It's as if our student from earlier decided not to study at all and failed the exam because they simply didn't know the material. But don't despair. It's not all doom and gloom. The beauty of machine learning is that it's a fine art of balance. Our goal is not to create a model that knows too much or too little, but to find that sweet spot in between. This perfect balance is where our model learns just the right amount from the training data. It understands the general patterns without getting bogged down in the specifics, and it can apply this knowledge to new unseen data with impressive accuracy. The key is to find the sweet spot between overfitting and underfitting, where our model learns just the right amount from the training data. How can we avoid these pitfalls in machine learning? Is there a secret sauce? Well, there's no magic bullet, but there are several techniques that can help us steer clear of overfitting and underfitting. First off, let's talk about cross-validation. Cross-validation is like a safety net for our model. Instead of training our model once, we train it several times on different subsets of our data. This way, we can ensure our model performs well, not just on one particular set, but on various ones. It's like studying for a test by practicing with different kinds of questions, not just the ones at the end of the chapter. Next on our list is regularization. Think of regularization as a sort of balancing act. It adds a penalty term to the loss function, which discourages the model from learning overly complex patterns that might not generalize well to unseen data. Essentially, it nudges the model to keep things simple, focusing on the bigger picture, rather than getting hung up on every minute detail. Lastly, let's touch on the importance of choosing the right model complexity. It's like picking the right tool for the job. If your task is to open a bottle of wine, you wouldn't use a sledgehammer, right? Similarly, for a simple problem, a simple model might suffice, while a complex problem might require a more sophisticated model. It's all about finding that sweet spot between underfitting and overfitting. But remember, these are just tools in your toolbox. They can help you avoid overfitting and underfitting, but they can't guarantee a perfect model. It's essential to keep experimenting, testing, and refining your model based on the results. So is there a secret sauce to avoiding overfitting and underfitting? Well, the secret sauce is really just a blend of careful planning, thoughtful selection of techniques, and persistent fine-tuning. Remember, the goal is not to create a model that just memorizes or skims through the data, but to build one that truly understands and learns from it. So now you know what overfitting and underfitting is, and how they can be avoided. We've delved deep into these two crucial concepts that can make or break a machine learning model. Overfitting, the act of a model learning your training data too well, to the point where it can't generalize to new data. And underfitting, where your model is too simple to capture the complexity of your data, resulting in poor performance. We've also explored the consequences of both overfitting and underfitting and how they can lead to inaccurate predictions and a lack of reliability in your models. But most importantly, we've learned how to avoid these pitfalls through techniques such as cross-validation, regularization, and early stopping. The world of machine learning is vast and complex, but understanding these core concepts is a major step towards mastering it. Remember, the best machine learning model is not the one that knows the most, but the one that learns the best. Happy learning.